Okay, let's get started. Okay, so today we'll go over MVT and some other properties of derivatives. So this says that, f continuous function on AB that is differentiable on open interval AB, then there exists at least one x such that f of b minus f of a over b minus a is f prime of x. So, I mean, a corollary of this is Rolle's, which pretty much is when f of b is f of a. But the at least part is clear, right? So, for example, if f of b was f of a, like let's say this is, b, this is, some point where, so f of a is f of b, like certainly like here you're basically asking the slope is 0, right? So certainly you could have more than one, right? So here, slope 0, I have like five of them. So you see, it's not unique, but there is at least one. So, and another corollary you can show is if f is differentiable on AB and I am 0 for all x in AB, then I am constant. So note it's not true for a point, right? You need that it's on an interval. So like here, it's 0 at this point, right? At like these points, but it's clearly not constant. So to be constant, you need to be 0 on like a whole interval. Okay, so let's continue. Definition, let f be real valued function on interval I. So real value just means the output takes values in R. So we're not mapping to like infinity or anything like that. So f is strictly increasing if and only if for all x1, x2, and I, the interval I, x1 less than x2, then f of x1 strictly less than f of x2. So that the strict is the no equality part. No equality. And similarly, f is strictly decreasing. So this is on I, yeah. So if and only if,
it's not my father. My parents live in California, okay? Wait. This is Hawaii. I'm on vacation. It's not my father.
I learned I could do this. I did not know that. Okay. So let's continue. So f is increasing on I. So increasing is just same as strictly, but you have equality, right? So Now, x1 less than or equal to f of x2. And lastly, decreasing. Bigger than or equal to. So hopefully this is clear, but in the case where we are differentiable, so f differentiable, this statement just means f prime of x is bigger than 0. On I, right, same thing here. I'll just put this, f prime of x less than 0 on I. Here, it's increasing means I'm bigger than or equal to 0 on I. And decreasing means less than or equal to 0 on I. Hopefully that's clear, right? if you think of a line has slope 1. If you imagine how it looks like, it's like increasing. Okay, so IVT for derivatives. So this part's important. So let f be differentiable on AB. And then I'm basically just going to write the IVT property. If A less than x1 less than x2 less than B, C is between f prime of x1 and f prime of x2, then there exists at least, again, it's at least one x in x1, x2, such that f prime of x is C. So, okay, so quick question here. Why did I have to write out this whole IVT, property? Basically my question is, would it be wrong to just say, let f be differentiable on AB, then f prime satisfies IVT? Because the statement, the second sentence here is just the result of IVT, right? So can anyone tell me, is it right or wrong to just say, f prime satisfies intermediate value theorem instead of writing this long second sentence? Any ideas? Yeah, any ideas? So I basically wrote a long, basically the IVT property, right? But why exactly do I, can I just write this, for example? Can I just write for second sentence, f prime satisfies IVT on AB instead of writing this long, this long thing, which is pretty much the result of IVT. Ooh, colors. Any ideas? No? Yes? Okay, so IVT is not a corollary of Rolle's theorem, but I don't think that's the question. But the point is, remember, IVT says what? F continuous on like AB, then blah blah blah, right? The IVT statement. So if I wrote f prime satisfied IVT, I would be saying f prime is continuous, right? But f prime need not be continuous, right? So example, I'm sure you had something similar on homework, but if f of x is x squared sine of 1 over x, And if f of x is this, you can check that at 0, the derivative exists, it's 0. And clearly, outside of 0, you can figure out what it is, right? Just product rule it. So 2x sine of, I'm pretty bad at this. And the derivative sine is cosine, right? So cosine of 1 over x, and I chain rule the 1 over x, I get negative 1 over x squared. So I should just get this, right? Someone correct me if I'm wrong. But basically, it's just product rule. So here, it's not continuous, right? You can check that the limit is not continuous at 0. But basically, it still satisfies this IVT property. So derivatives are nice, right? In the sense that they have the IVT property, but they don't, you can't just say it satisfies IVT, because to satisfy IVT, that would mean the derivative is continuous, which it's not. So yeah. Okay. Any questions so far, or everyone get it? Yeah, so I don't know what you mean by corollary of Rolle's theorem. So Rolle's theorem is a corollary of MVT. Yeah, okay. So let's start doing questions today. So just see how MVT is applied. So the first thing would be, let's do problem 2, cosine of x minus cosine of y, right? So 29.2. I want to show this is less than or equal to x minus y. So what does MVT give? MVT says, given x, y, and r, there exists z in x, y. So, without also generality, I'll write x smaller than y, yeah? Okay, so there exists z such that what? Cosine of x minus cosine of y over x minus y is basically, if I called, if f of x is cosine of x, then, f prime at z, right? But what's derivative of cosine? Derivative of cosine is just sine, right? So this is just, or negative sine, if you like. And this is certainly true, right? So is equal to negative sine of z times x minus y. But sine is bounded by 1. So this thing's certainly smaller than x minus y. So hopefully this isn't too hard. Yeah. Okay. Now let's do 29.3. So f differentiable on R, f of 0 is 0, f of 1 is 1, f of 2 is 1. So f differentiable on R, f of 0 is 0, f of 1 is 1, Show f prime of x is equal to a half for some x in 0, 2. Okay, any ideas on how to do this? So this is an MVT question. So how am I going to get the fraction 1 over 2? You can talk. Yeah, if f prime is continuous, you can use IVT, but what does IVT say? It just says you get every value in between. So what I'm saying is, even if f prime is not continuous, it has that IVT property, right? So here, like, this holds for any derivative, right? All I need is that it's differentiable. So I don't need anything about the derivative. Like, the derivative could be discontinuous everywhere, but it will satisfy IVT. So, okay. So, yeah, so for the mean value theorem, right? I mean, I have change in sort of here, like change in image over change in domain, right? I want my change in domain to be like the denominator is change in domain, right? I want my denominator to be 2. So it's pretty clear I'm going to use 2 minus 0, right? So, I mean, that's pretty, so there exists z in 0, 2 such that f of 2 minus f of 0, 2 minus 0. So by MVT, right? So here I get 1 minus 0 over 2 minus 0, right? So we are done. Okay. Now let's continue. So we increase function from 0 to 1. No. Your function might need not be increasing, right? Because I only know the value at 3 points. So it could act crazy between 0 and 1 for all I know. So it need not be true f is increasing. Okay, so the next question is show f prime of x is 1 over 7 for some x in 0, 2. Okay, so we know we found a point such that I am a half. So how am I going to get 1/7? Any ideas? So obviously it's not MVT, right? Because there's no way I'm going to get a 7 in the denominator. So we're clearly going to have to use the IVT for derivatives, right? So it's basically the intermediate value property, right? I have a value where I am a half, which is certainly bigger than 1 over 7. So if I find a value where my derivative is smaller than 1 over 7, then the IVT property for derivatives gives me that there's some point such that I am 1 over 7, right? So all I need is some value where I am less than, 1 over 7. And you could get that by MVT used for f of 1 and f of 2. So by MVT, I use z tilde in 1, 2 such that f of 2 minus f of 1 over 2 minus 1 is f prime of z tilde. But f of 2, f of 1 is the same, right? It's Rolle's theorem. They're the same. It's 1 minus 1, right? So this is 0. So I have a point where my derivative is a half and a point where my derivative is 0. So by IVT for derivatives. So keep in mind the statement of this is not f prime satisfies IVT, right? So I gave a counterexample on top, but that's what they call it. So by IVT for derivatives, there exists, I don't know, z hat such that f prime of z hat is 1 over 7. Okay. Any questions so far? Hopefully that is clear. Okay. So let's continue on. Let's get more used to, mean value theorem. So let's do 29.5. So f defined on R and f of x minus f of y is less than or equal to x minus y squared for all x, y, and r. Prove f is constant. So let me just write the question. F defined on R, and I have f of x minus f of y is less than or equal to x minus y squared for all x, y, and r. And I want to show f is constant. So how do I show something's constant, right? So if we go back, I need to show that I'm 0, right? Right here, the corollary, this part. If I'm 0 on an interval, then I'm constant, right? Here I want to show I'm constant on all of R, which is the interval negative infinity to infinity, which is still an interval. So we basically have to show our derivative is 0. But a priori, right, let me just write, we don't know f is differentiable yet. The problem never gave that to us, right? So we have to somehow use the top to get that it's differentiable and it's 0. So what we're going to do is we're going to let y naught be in R. So y naught is any point in R, right? So what's the definition to show it's differentiable at R? We want to show, this limit exists, right? X goes to y naught f of x naught x minus, I'm going to take absolute value. I'll sort of explain why, but it's enough to show if this exists, then if this is 0, then without the absolute value, it's 0, right? So let's show this. So this thing, on one hand, is less than this, right? By the property above. So by this thing. If I just divide out by absolute value of x minus y, we have that property, right? On the other hand, if I take absolute value, I'm always bigger than or equal to 0. Agree? So you're gonna get, this thing goes to 0, right? If you plug in y naught for x. So this goes to 0 by squeeze theorem. In particular, this is just, if you bring the limit inside, it's just this, right? So that means that, if absolute value is 0, it just means this is 0, right? The only number that has absolute value 0 is 0. And from here, y naught was arbitrary, right? Was arbitrary. Right, so here I'm using the fact this holds for all x, y, and r, right? So y naught is arbitrary, so f prime of x equals 0 for all x and r. So f is constant. Yeah, so I feel majority of this is just MVT. So let's do 2 more. I'll try to pick even ones. So there's one that's very important that you all should know, and that's the last problem. It's pretty important. So, but before that, let's do one more just so we're all satisfied with MVT. let's do 14. So f differentiable and its derivative is bounded for x and r, and f of 0 is 0. We want to show f of x is bounded by these two functions. So again, let me just write it out, right? So f differentiable on r, 1 less than or equal to f prime of x less than or equal to 2. And f of 0 is 0. So we want to prove x less than or equal to f of x less than or equal to 2x for all x bigger than or equal to 0. So clearly it's at 0. This is true, right? Because if I plug in x equals 0, I get this, which is 0. And certainly we're given that this is 0, right? So right here, we're given that. So it's certainly true for x equals 0. So let's consider x bigger than 0, right? Fix any x bigger than 0. Fix. Then since we're differentiable, then, you know, MVT gives there exists x tilde in 0x such that f of x minus f of 0 minus 0 is f prime at x tilde, right? So but f of 0 is 0. So you just get this. And then you're done, because what is my derivative bounded by? It's bounded by 1 and 2. So this is bounded by 2, this is bounded by 1. And then you multiply the x, right? So hopefully it's not that hard. Okay, is everyone comfortable with MVT? So we're going to be getting into the hardest question of today. It's pretty long, but it's very important. So everyone clear so far? Okay, so this might take a while. So let's sort of read what it's saying. So 29.18, f is differentiable, and basically my derivative is bounded by 1, and it never reaches 1. So my derivative in absolute value is like always smaller than 1. And in fact, it never reaches 1. Like there's no sequence going to 1 because the soup is smaller. And basically, part A is basically helping you show part B. So in general, if you're given a function, it need not be the case that you have a fixed point, right? Like, you know, f of s is s. So, I mean, certainly it's true for, I guess there's one thing where you could do like for continuous functions, but here's another way using Cauchy sequences. So, okay, f differentiable on R. On R, and A equals soup f prime of x in R less than 1. So a priori, if this number is less than 1, why do we like numbers less than 1? Well, what can you tell me about this? What can anyone tell me about this? When A is, you know, less than, and certainly is positive, right? Because every term here is positive because I'm taking absolute value. So it's some positive number between 0 and 1. So this is a geometric series, right? And geometric series converge like for, you know, values between -1 and 1, right? So converges, and hopefully you could show by limit definition that this means that the tail goes to 0, right? It means for all epsilon, I'll use epsilon 1 because I'm going to use epsilon later. So bigger than 0, there exists n1 in n such that for n bigger than n1, you know, k equals n to infinity, right? So I'll put bigger than or equal to, just to make stuff. So in particular, you know, just to make stuff easy. In particular, you know, for n1, it's true, yeah? So series converging means the tail goes to 0. So we'll sort of see why we need that. So the question for part A is we define Sn to be f of Sn minus 1. And S naught is just some value in R, right? So, you know, S1 is f of S naught. S2 is f of, it's like some recurring sequence, right? This is S2. Okay, so want to show Sn converges. Now, I don't know what this limit is, so I can't really use the normal epsilon definition. So how do you show a sequence converges? Anyone remember? What's that? Yeah, it converges because A is smaller than 1, Joseph. Right here. I'm using this fact, right? So like an example would be like, you know, this thing converges, right? Because 1/2 has absolute value smaller than 1, but certainly this thing doesn't converge, right? So I mean, I'm just using the fact that it's some number between 0 and 1. But yeah. Okay. So back to the question. How do you show a sequence converges if you don't know what the limit will be? Anyone? Yeah, exactly. Show its Cauchy, right? So but before we show its Cauchy, let's sort of see how these interact, because you'll see it interacts pretty well. So this f of Sn plus 1, by definition, is just f of Sn, right? So scratch word. Right? So, but then f of Sn is just this, right? You know, just by definition. And by MVT, this is just f prime at x tilde times Sn minus 1. Agree? Now, my derivative is bounded by A, right? Because A is the soup of all derivatives. So this is smaller than or equal to A times Sn minus 1. So we have a relation from n plus 1 to n to n minus 1, right? And you can keep going, right? You can sort of see this power 1, just for reality check, if you add the 1 and n minus 1, you get n. So the power corresponds to, you know, if you want to, so I could keep doing this, right? I could say it's less than or equal to a squared Sn minus 1 minus Sn minus 2. I can keep going, right? By the same argument. So what you're going to get is Sn plus 1 minus Sn is less than or equal to a to the n S1 minus S0. If you go all the way to the bottom, right? Again, reality check, these two should add up to n, right? Like here, 2 plus n minus 2 should be n. Just so we get the power correct. Okay, so let's show its Cauchy now. So want to show for all epsilon bigger than 0, there exists n and n such that for, without loss of generality, I'll say n bigger than or equal to m. You know, n's the bigger one. For n greater than n, we have this, right? Sn minus Sm is less than epsilon, right? So is everyone clear so far? Okay, good. Now, what we're going to do is I am going to choose to let epsilon be bigger than 0. And I'm going to let my epsilon 1 to be epsilon over S1 minus S0. So my epsilon 1 was, remember, the tail, right? I have this statement since the geometric series converges. Oh, sorry. This should be epsilon 1. But yeah. So I'm going to choose my epsilon 1 to be epsilon over S1 minus S0. So you'll see why I do that. So this because I did the scratch work beforehand. But so we have that then whoa then there exists n1, right, such that sum k equals n1 to infinity a to the k is less than epsilon over this, right? Because this is what I get from just this geometric series converges. So I'm going to choose my n, right? My n to be n1. And let's see how things turn out. So Sn minus Sm, I'm going to write this. I'm going to subtract Sn minus 1 plus Sn minus 1, subtract Sn minus 2, add Sn minus 2, and, just keep going. So all the way to the bottom, right? Sm plus 1. So I didn't change anything, right? Because I added and subtracted this. Subtracted and added the same terms. And hopefully you all see what's going to happen, right? Triangle inequality. I'll just do this. Okay. Now, each one from our scratch work was less than or equal to what? From scratch work, right here. Sn plus 1 minus Sn is smaller than a to the n times S1 minus S0. So this one's, a to the n minus 1. Right, because I go with this exponent, right? So this exponent matches like this exponent. So yeah, so I go with the n minus 1 exponent. A to the n minus 2, S1 minus S0, all the way to what? A to the m. So if I factor out the S1 minus S0, this is just this, right? I'm summing from m to n minus 1, right? A to the k. Okay, but this is certainly smaller than, m is bigger than n, right? So right here. So it's certainly smaller than if I just started at n, capital N, right? And it's certainly smaller than if I just add all the terms to infinity, right? But this guy was smaller than what? We chose it, so this was smaller than epsilon over S1 minus S0. So So we're done, right? We're smaller than epsilon. Sorry, smaller. So the S1 minus S0 didn't matter. I just needed a fixed thing, right? Something that didn't depend on, you could have done S2 minus S1. Your power of A would have just changed. But in the end, like you just need something that doesn't depend on N and M. So, okay. So that's the hard part. So sequence converges. Now here's the easy part. Show there exists S and R such that f of S is S. So let me see if anyone has questions. No, great. This is easy because what was this sequence? It was this sequence, right? Now let's take limit on both sides without loss of generality. Since our sequence converges, let's say Sn converges to S, yeah? Let's call the limit S, right? We showed it converged, so. Now, on one hand, this thing is S by definition. Now, F was assumed to be what? Here, we didn't use our last assumption. It was differentiable. Well, we sort of used it to, for the soup to make sense. But in particular, if we're differentiable, we are continuous. So continuous means, by definition, it means this, right? We could bring the limit inside, right? It's the value of the function at the point. And voila, you have f of S is S. So in general, this is called the contraction principle. So there's a more general statement. It's called the contraction principle. Pretty important in real analysis. I mean, finding fixed point is pretty nice. Okay. Any questions on this? So again, here, if you remember the definition of, continuity, it's this, right? Where so it just means you plug it in, right? So I'm pretty much using that. So, okay, any questions so far? Great. Okay, so let me just remind you, just for quiz, I forgot the number, 8. So I think I'm just gonna do one quiz for now because I think Neil expects 10. And I think the reason he expects 10 is so he could drop like 2 of them. But okay, so quiz 8. I think we're on track to have 10 quizzes. So I'll just give 1 a week from now on. So right, I think it's quiz 8. So for here, it's just gonna be on derivatives, right? So particularly the thing I'm going over today. So MVT, IVT for derivatives, like, what it means to be increasing, right? Like f prime bigger than 0 means you're increasing. And then it's gonna, I'm gonna test on the L'Hopital. That's the next section. So I made this quiz 6 o'clock start on Wednesday. So it won't start at 2. Yeah. So it'll start at 6 because at 5, that's discussion. And I'll be going over L'Hopital really quick. Only like one part of the quiz is on L'Hopital, like one part of the question. So most of it will be here. Yeah. Okay. Any questions for today? Okay, great. Yeah, so study the chapter 29 pretty much, 29 and 30. I think IVT is 30. I mean, L'Hopital is 30. So